And the reality is 1 degree, you're 1 million and some odd miles off the sun.
Yeah.
The reality.
So?
That's calculated. Well, you're not looking at the sun no more. You pulled yourself off the sun.
You keep on saying that.
And this is what I say. You got to do the field work. You got to
field work matches the. This is what I don't know how many times I can say it. Your field work matches the globe predictions. What it does not match is your description of the 45-degree sector test.
You got to know your limitation. You don't know your limit. So how do you know your correct?
What does that mean? I know the angle. What do you mean when you say know your limit? I think you mean
at 1 degree.
You mean there's a minimum angle.
Yeah, at 1 degree off the sun from 45, in other words, 46 degrees. What's your distance or your fan off the sun? Your line, your visual line. It's 1 million miles. You're off the sun. You can't.
Yeah. Right.
You've exceeded your model's length, and now you're telling me that sun.org, they're just confirming it.
They're confirming that your understanding of the model is wrong.
You don't understand observer angle.
Way back in the beginning, we agreed to that there were two possibilities: that the model was incorrect, or that your understanding of the model was incorrect. And now you're rejecting the second possibility.
No, I'm not rejecting. I'm saying you don't know.
Is it possible that you misunderstood?
Is it possible that you don't understand observer angle?
Well, since that's a term you made up, yeah, it's possible. I don't know what you mean.
Term.
Yes, it is.
Observer angle. What angle are you to that object at 3 hours? You're 45 degrees.
No, you are not.
The sun survey point says you are.
No, it does not. It says 49 degrees.
It sure does.
This is the formula. Do you understand that this is the formula?
Do you understand?
How do you feel about this formula? Tell me what you think about this formula.
How are you going to break it down? How do you break it down into sector? Break it down into sector.
Break it down into sectors.
45-degree sector. Break it down. What's your time?
Break it down into 45-degree sectors. I would say the best way to visualize the breakdown.
Do it your way. Tell me how you do it.
How would I do it? I take the fact that the sun, I started with putting the sun and the earth on an axis, XYZ, and just said, okay, put the sun straight down the x-axis. And then I said, okay, we're going to tilt the earth 23.5 degrees. Where does that put the sun's light on the earth, right? Just tilt it like that, right? Well, it's pretty straightforward.
When you talk about sunlight now, you're talking a pretty illuminate. You're talking about sun illumination. That's a broad area.
No. Where is the exact subsolar point?
You're talking about the contact point.
Where is this point that I'm pointing to, right? Mm-hmm. Like the diagrams. I don't mean the whole half of the earth that's lit.
Yeah.
Okay, the center point of that half.
Degrees?
Okay, and so how did I do that? When I did it, I did it with linear algebra. I did a matrix. I did a rotation of the Earth. So that's where you get the sine and the cosine of delta. Okay?
Okay.
That comes from doing this. All right, and then I said, yeah, but the observer is somewhere on the Earth. So it does another rotation. So I'm going to want to take the observer and put them there. And now I want to align this whole thing so that the observer is the one that's straight. So I have to do another rotation for the observer's latitude. And that is where the sine and the cosine of phi come.
Yeah, you just invalidated your process. In other words, you've changed it twice. In other words, you've changed the observer position twice. You got to go from the original observer position from the time.
I can do the math either way. I can either work the math from the prospect that the observer is at 0 degrees and the sun is at some other angle, or I could go from the position that the sun is at 0 degrees and I am at some other angle. You can go back and forth.
Why would you do 0? Then you're going to run into atmospherics.
Yeah. You don't You don't seem to be following me. Every angle is relative. Can you agree to that?
Well, every angle is important, but
Every angle must be referenced to something. There's no such thing as an absolute angle.
and that's why we use grid magnetic as a start point.
Okay.
Or grid magnetic. So we want that linear, we want that line of reference. In other words, we need to set the geometric edge. And then that's how we can start our test with timing and position. So yeah, I would say that, you know, you're kind of there in your understanding of it, but again, you're negating, which a lot of heliocentrists do, and that is observer angle is critical. And the reason
the observer angle is right here.
Angle is critical.
It's called phi.
It's part of the process.
It's called phi and also HRA. There are two observer angles in this.
We can't negate it. You know, the heliocentrists, they like to negate it. And it's like, well, I don't. What do you mean observer angle? And it's like, well, your model, you're at an angle. We look at 45 degrees longitude. You're 45 degrees to that object.
You ask, what is the observer angle? There are two angles. The one is your latitude.
Yeah, there's more.
Latitude is here. You see, it's called phi.
Mm-hmm.
And then the other one is throughout the day. You go around, right? The Earth does this rotation throughout the day. That's HRA. So there are two observer angles in this formula.
Excuse me.
Okay. So it's not a matter of I don't understand the observer angle. They're here. Right? There's one of them, which is your latitude, and the other one is the Earth's rotation throughout the day. Right?
Well, yeah, the rotation is going to tell you what your observer angle is based on timing. So
correct. Again, so okay, there you go. That's right there, HRA.
So again, you're looking.
Tell me I don't understand it. It's right here.
Yeah, that's what I'm saying. 45 degrees. Especially when you're when you're looking down at your rings along the equator.
Exactly. That's where the 45 degrees goes right here in the HRA. That's where you put 45 degrees. You put that right there. Put 45 degrees right in there. Then put your latitude, and then put the sun's declination for that day in there. All right. And then you grind this out on a calculator and you find out what you get. You don't get always less than 45 degrees. I mean, just simply think about it. On the North Pole, it's always at 23.5 degrees.
Well, you can't. And again, your process is, yeah. You take your observer angle. That's why you got two numbers in the test box. Your bottom number is observer angle. Your top number is your maximum that you can exceed for that model. In other words, you've exceeded the line of peril.
And I will set those limits at the error tolerance of your measurement technique and apparatus. That is the tolerance. It will be centered on the correct answer, which in this case is 49 degrees.
Not according to a right triangle calculation from your sun, your heliocentric sun at its distance, you've exceeded it. At 1 degree.
Isn't a right triangle. There are no, do you see any right triangles?
Sure.
Where is this right triangle you're imagining?
Well, you have to calculate based on that model's sun's distance.
It's not a right triangle.
What I'm talking about is the right triangle that I provided you.
That was a mistake. That's what I keep trying to tell you. 45, your right triangle that you modeled,
Matt,
is not the correct model. Do you think that this is not the correct model over here?
You got to check that measurement against the model. The model's sun at its set size and distance.
Here's the model. Here's the model, right?
You can't just throw
that's the globe model.
Lines out there and say, well, this is going to work because this is it. Well, you got to look at the sun's size and distance in the heliocentric model.
Hold on. I'm just saying you're not being condescending. It's stress.
You got to look at that, Matt.
What do I have to look at? I'm sorry.
You got to look at your sun size at its distance for your heliocentric model. If you're using the
the sun size is a half a degree, right?
No. What you got to look at is you plug in what you've exceeded line of parallel at the sun size at the distance.
You keep saying that like it's some kind of prayer recital or something. It isn't. The model says 49, not 45.
Well, you can't. You
made a mistake, and you just need to go back and find it. Right? You made a right angle triangle. Please point out to me on the actual model. Here it is over here. The actual model. Mm-hmm. Where is the right angle you're even talking about? There are no right angles here.
Sure, right triangle. When you look at the sun and you look at what it exceeds for its limit. So let's go to.
Now, hold on. You can't just declare that there is a limit. If there is a limit, you need to derive where that came from.
Size. Go to number 17 on your printout that I gave you. All right, stop right there. Go right there. Up one. All right. Now let's talk about the right triangle calculation, because this is what you hear.
Where is the right triangle?
Well, you need to know that, because that's going to find your limit. In other words, what you've exceeded, your angle, your observer angle plus your measured angle, those are your composite. So in other words, 45 and 45 is 90 degrees. So now your line of parallel at 1 degree over 46 degrees, you've exceeded 1 degree. At 1 degree at the sun's distance at 93,879 and some change, your 1 million mile, your fan is off. In other words, your line goes off the sun. Your visual line, that line that's to the left there where it's got the little cross, that's now your visual reference line. You are off the sun at 1 degree. So now you just invalidated your model by telling me, well, you're agreeing with me. You've just invalidated your model.
It's funny to hear you say that. Do you understand that this whole sheet here is based on that 45-degree angle that you said was true?
That's why it's called the 45-degree sector test. You're testing the 45 degrees.
It's not, the model does not say 45 degrees.
Well, that test is. It's a 45-degree sector test.
The entire test is called the 45-degree sector test. It's
now go down to the next one. Go down to the next diagram. You got to know your model's limits, Matt, and you don't understand that. You got to understand it. Now, if we use the right triangle calculation at 6.6 degrees or at 51.6, the maximum reading, you are 6.6 degrees exceeded line of parallel. That is 10,860,000 miles and some change. You're way off.
All right.
The sun.
Let's pause, because Rob has a question. He says, where does the 45 degree come from? This one right here, 45 degrees. This is where you get the 6.6, right? You said 6.6 is wrong because you measured 51.6. You subtract the 45. Where does 45 come from?
So look at your little numbers above it where it says line of parallel. So you got 45 and 45. The bottom number is your observer angle to that object at that time. Your top number is your measured angle. So you can get 45 degrees to the sun and still be on the sun. You're okay at 45 degrees. At 46, you go off the sun. You're pulled off the sun.
Right. Uncle Drunkle's Country Cabin says, I think he's using a standard 15 degree and 3 hours. Is that right?
That would correlate out to it.
Right. What if I told you that in 3 dimensions, the sun does move at 15 degrees per hour, but not straight up and down?
Well, you're not.
It also goes to the side. Did you notice that the sun goes, some of it goes up and down?
You're not measuring. You're measuring at position. It's got to be in that window. In other words, when you look at that window in the sky, if that sun is too high in the sky, you're measuring it off a flat surface. It's the reason I told you, look, when you look at a picture in your living room from a recliner straight up, okay, that is going to be straight on. When you recline back, what does that do? It drops it. That sun's got to be low in the sky. If you're
let's do an exercise. Let's do an exercise. Okay, pick a point directly in front of you. your camera, probably. Look at your camera,
Mhm.
and now lean back 45 degrees. Lean back 45 degrees. The camera has lowered 45 degrees. Agreed?
Yeah, that's
Okay.
correct.
Now, let's lean. Let's not lean back. Let's tilt sideways 45 degrees. The elevation of your camera is still level with your eyes. Agreed?
At 45 degree. Now, what are you talking about?
I'm rotating now on azimuth, 45 degrees.
Are you
45 degrees to the camera?
Are you talking about when you're leaned back or when
No,
you're
I'm not leaned back. I'm not leaned back.
okay?
First, I leaned back.
Forward.
First, I lean back. Now I go sideways. Only sideways. The elevation angle of the camera is still what I would call 0. Agreed?
If you're at 45 degrees, yeah, you're going to be at 0. Yeah.
Okay. That right there shows why your 45 degree sector test is wrong. Let's now combine them. Let's combine them. Let's say I'm going to move 45 degrees, and let's take 15 of those 45. We're going to be in the up and down direction, and about what is the rest? 30 is going to go in the side direction. So I'm going to go up 15 and over 30. So this is 45 degrees now this way, 45 degrees that way. And I know my math it's an approximation. 45 degrees at a diagonal, please. Go ahead. 45 degrees at a diagonal. Is the camera below 45 degrees? Of course, right? You didn't go up and down 45 degrees. You went in a diagonal.
Okay, so I see your problem now. So when you talk about your diagonal, yeah, you're doing what's in the military science or in what survey is called a graphic traverse. So when you traverse on, you're traversing on at, because your sector limit is set by your east and west movement, and then you're going to measure your sun height. So now at 45 degrees, you're going to have a line of parallel. In other words, you can't exceed from that position. You can't go 46 or more, because remember, your angle of the observer, you're already at 45.
We're not questioning the 46. We're questioning the 45 that you started with, right? The 45 is the core mistake. Your mistake is that you think it's 15 degrees per hour on this axis.
No.
It is not.
No.
It is 15 degrees per hour diagonal.
We're talking east-west. Yeah, see, and that's where you get it wrong.
It's neither east-west nor up-down. It's diagonal. It's both east-west and up-down combined.
Again,
the actual motion of the sun will be like that.
Yeah.
Right? Why don't you do that with your arm with me? Go ahead. Like, I'm doing it. Don't be shy. Sunrise. Okay, actually, for me, sunrise. It's going to go up over the south, and it's going to set over there. Right?
Yeah, that's what the sun is going to do. And there's actual diagram.
Go ahead and do the arm exercise, please. Go show us all that you're with us, and right. Sunrises for you. Where does the sun rise for you?
So,
don't want to do it.
When we look at our sector test, okay, remember that the sun is always 90 degrees when we're looking at that sector. Okay, so now if I'm, how do I get make sure? If I'm here,
the backwards camera is hard.
Oh, it's a son of a gun.
Okay. I know. I get twisted around.
So my sun, if I'm here, let me get that. If I'm here, that sun has moved in the opposite direction. Man, this might be challenging here.
I think you can reverse. I think you can reverse your camera, maybe. I'm looking real quick.
So, anyway, we have a start point.
I don't see it.
Yeah, we have a start point, and then we have 3 hours. Okay, so that position. So I think what confuses people is when you talk about the up and down in the east and west, and there's a diagram if you look on number 7. on your printout. Right there, go back. And how a line of parallel occurs with the sun, okay? So, and that's what you talked about your observer. Now you can talk about your east and west, and it also gives you the sun contact point. And again, this is a three-dimensional image. So when we talk about sectors, we're looking at the geometrics of it, okay? So this is how we get our observer angle, okay? Now you're contending that it's not a perfect 45 degrees. No, you can contend that. But again, you have to understand what your line of parallel, in other words, what's your limit to the sun, because when you go above 45 degrees at your angle, the observer angle, you're pulling off the sun. So your sun width is indicated by your arrows, your black arrows. Your observer angle when you measure is 45 degrees. Once you start going from that 45 to the outside of the sun, which is about 45.3.4, you get separation. In other words, you're no longer looking at the sun.
You would get separation if you get off of the angle to the center of the sun. But the angle to the center of the sun is not 45 degrees. That is incorrect. So just stick to that. Just stick to where you got the 45 degrees. Don't go on past it, because
you have to understand
you're already off, right?
If you don't understand line of parallel, you'll never understand that. And that's your limit. You have to know your limit. What you're telling me is
I'm not going to argue with you about the limit. What I'm arguing is that your 45 degrees that you've based all this on is not correct. So from that point forward, the rest of it is bunk.
So what you say is, yeah, the 45 doesn't exist. However, the sun survey point timing all says different, especially if you're going from a spherical.
Especially the globe model does not say.
Oh, you most certainly are.
Especially the globe model doesn't say that.
Oh, sure does.
It's my model, right? I get to say what my model says. My model says that the Earth is tilted 23 and a half degrees towards the sun in the summer, right? So this assumption that the sun should move 45 degrees per hour on this axis is not true.
That's left and right.
At this axis.
Hold up, time out. Go
diagonal
back.
Across the ball.
Go back. No. That's, and again, see, you're let's get you straight, because right away you're talking about something that's entirely different.
I'm talking about the globe model. That's the globe model. This is my model. I don't know what you're talking. That's the globe model.
Go to section 1 where we go to the sun survey point. There's a diagram on there I need to show you. Keep going down below that. Right there. Okay, stop. All right. So that's what we're talking about, the sector. You look at the OS. The OS, when you start from your line of magnetic north-south, that's just your position. That's your east-west.
Okay.
When you take your measurement, you're measuring across the 45-degree sector. Okay? You understand that? So just make sure we're clear. Because what you were talking about is, well, you're talking about, no, you're starting from one sector, then you're going to measure the sun position in the sky from the other edge of the 45-degree sector.
What's a sector? Define sector. You keep throwing that word around as if we would know what that is. What does that mean to you?
So in other words, you look at that fan, that's 45 degrees. In other words, that's based on, that's the globe model broken down into sectors. In other words, 8 3-hour sectors at 45 degrees.
Okay.
And
let's look at the globe model now and look at that in terms of sectors. The sectors are not parallel to the east-west. It's not. We're not talking about east-west.
Well, we're not talking parallel. Go back to the diagram. That's not parallel. We're not talking about parallel.
We're talking about these rings through that pole. If you look straight down that pole, can I look straight down that pole? I don't know if I can. And you divide that into a pizza. That's what we're talking about.
Right, and that's what I'm showing you right there. From the top down, if you go back to that diagram, that's the view from top down.
But the problem is the sun doesn't light. It's not the equinox. It's not the equinox all year round.
Well, we're not
If
talking.
it were the equinox, you'd be right.
Right now, the conversation, we were talking about the east and west sector, the distance. So that's what
What I'm saying is the sun does not move east to west.
Well, I mean, your globe, as you're spinning, it's going to move that sun is going to move east to west.
And it will also rise and fall during that same time. Agreed? So one way to say it is the sun moved east to west. Okay. The sun also rose and fell.
You'll have to explain that.
In the morning, the sun's down low.
Mm-hmm.
At noon, the sun's up high. At night, the sun's down low.
Mm-hmm.
All true. Also true. In the morning, the sun's in the east. At noon, the sun's to the south.
Mm-hmm.
And at night, the sun is in the west.
Mm-hmm. Okay.
So the sun went east to west. At the same time it was doing that, it went up and down. So to correctly describe the sun's motion, either one of those alone does not describe the sun's motion. Together, they describe the sun's motion. The sun, it goes low east, high south, low west. If you do, I swear to God, if you do that motion that I just did,
mm-hmm.
I think you might start to understand where you went wrong. Because the sun's motion is diagonal. And we all know that it is diagonal.
Well, that's the diagram. That's showing you diagonal. In other words, you need to understand your line of parallel. Again, you got to understand your line of parallel.
Starts there, up here, down there. So it's moving at 15 degrees an hour at a diagonal rotation. Right? 15 degrees an hour. It starts here. Then an hour later, 15 degrees. Hour later, 15 degrees. So now I've gone 45 degrees. Right? After 3 hours, I've gone 45 degrees. But I didn't go 45 degrees this way. I went 45 degrees that way. So at a diagonal angle.
When I look at the heliocentric model, they're showing the sun as moving through the universe straight. And the Earth is orbiting around the sun. So now you're going to have to explain how you say all of a sudden the sun is doing loop-de-loops going through the universe, because as most what I see is the sun is going straight.
Okay.
And as we see that from visual perspective, that sun comes across our sky. Now it looks like it elevates, but it actually is just coming across our sky based on its position. Now it'll look like it's raising, but the sun is actually just going across our visual perspective.
Are we changing topics now?
No, well, I'm just talking. You said the sun elevates, so I'm saying, well,
yeah, that's my perception.
When we look at
on the ground,
the heliocentric model, show me where the sun's doing loop-de-loops and it's changing as it's going through the universe. At how fast does it go through the universe?
Right.
How fast? I don't know. I'm just asking.
I know. I don't know. Maybe Rob, you got it off the top of your head. What is the speed of the CMB?
100,000 some odd miles or 700,000 miles an hour.
I don't know. It's freaking fast.
Yeah, fast. So now you're telling me that the sun it's not going straight. It's doing loop-de-loops in order to.
I'm not saying that.
Well, it's got to now because you're saying it elevates.
Relative to me, yes.
That's
I measure an angle. I don't know about the rest of you all.
You're talking about
an angle. It's relative to myself.
Right,
it's
exactly.
Relative to my local vertical. I establish a vertical, and then I measure the angle.
What you're talking about is
I like to use the horizontal plane as my reference. So that's actually the vertical plus 90, right?
You're talking about visual perspective now. You're talking about that sun comes straight across the sky. Now, as it comes straight across the sky, it's going to look like it's elevating because it's coming closer to you. And when it gets to a point where it's 90 degrees to you, that's the high point or the solar noon. And then it moves away and it looks like it's lowering because it goes away from you. but it's on a straight, basically on a straight line.
I think you're trying to describe the flat Earth model.
I'm talking about the sun in your model too, because I don't see no loop-de-loops in the sun.
Well,
Show me where that, you don't have to show me tonight, but if you can give me a reference and show me where that sun is rising and lowering as it's traveling through the universe.
It's here
day,
next to you.
By
Next
20
on the left.
by 24 hours. I mean, I want to see that going a half million miles an
24
hour.
hours. You ready? 24 hours. We're going to do it. We're going to start from.
Well, no, I don't want to see that. I don't want to see that. Because you're showing me, I want to see the sun move. I want to see the sun path. In other words,
this is the sun path.
No, that you're showing me the Earth. Show me the sun path, because the diagrams that I see show the sun going straight through the universe. And it's moving.
It's not relevant to this discussion. That's not relevant to this discussion.
Planets are orbiting around it. So now you're telling me not only are the planets orbiting, because now you're talking about rise and fall. You're talking about the sun is rising and falling. Oh, by the way, 500,000 miles plus more miles an hour, and now it's doing these little shakes. It's going up and down as well.
No, that isn't what I said.
Well, you're talking about the sun's rising and falling.
Yeah, you know that the sun rises, right?
Well, that's the perspective that's coming across.
Okay,
straight across.
I'd like to ask you to just take a moment. I understand what's going on, but we're trying to have a collaborative discussion, and we have gotten pretty adversarial. So let's try to get back to collaborative. In collaborative, we would try to understand each other. Mm-hmm. So when I say the sun rises, I think you know what I mean. And I think you're being unfair to try to act like I'm saying the sun is physically moving up and down. We know that the sun visually rises, and this is not contentious. We understand that, right? Can we get back to that place?
Across our visual perspective, across the sky.
It starts in the east, low on the horizon. And then later on in the day, when I look, I'm going to see the sun. 3 hours later, the sun's going to be there. It's going to be farther to the south, and it's going to be higher up above the horizon. I'm not saying the sun is physically moving. I'm not saying it isn't. I'm actually not.
I'm glad you cleared that up, because that scared me there for a minute. I was like, how's the sun moving? So in other words, what you're telling me is at distance, you could put the sun like an abacus, a bead on an abacus or a line, and I could slide that line. In my visual perspective, that would show the sun's path.
No, it would not.
Really?
I'm afraid you're going to have to rotate it in your line will have to be a ring.
To get the correct look. You're talking about the firmament. It's like up in a dome, or
I'm talking about the globe Earth model. And I'm also talking about just what we see. If we forget about the models and just talk about what we see, maybe we can get back to
visual perspective. Now we're on visual perspective.
See that the sun starts here. Mm-hmm. And I notice you just will not point with me. I don't know why, but it's right there. Can you do that? Can you say, there's the sunrise? Where is sunrise?
To the east of me.
Point to the east. I don't know which way is east for you.
It'll be actually be this way. Wait.
Okay. And then 3 hours later, where is the sun? I say
closer.
For me, to this time of the year, it'll be right about there.
Okay.
Okay. And you'll notice my arm is higher above the horizon, and it has also moved to the south.
Okay. Keep going.
Okay. So let's go another 3 hours. We're at noon.
Mm-hmm.
The sun is due south and at some angle above the horizon.
Okay.
Higher than it was earlier, right?
Mm-hmm.
And then 3 hours later, and then finally, sun will set in the west, right?
Yep.
And actually, when I say 3 hours later, the reality is it's winter here, so it actually won't be 12 hours to do the traversal.
No, it'll
be like 9 hours to do the traversal or something.
So you're talking about distance and visual perspective. So in other words, I could put that sun on a string and just run it across you and tell you and ask you, I could do this experiment and say, is that sun rising or falling? if you couldn't see the string, would you be able to say yes or no? You wouldn't be able to, because as that sun gets closer to you, it gives the visual perspective that it's rising, but all it is it's positioned to you as changes. So it comes across our visual perspective.